Okay, so last time we introduced the Pythagorean theorem. So if we have displacement, the distance between these 2 points given by the distance this new point, it has the same y coordinate as the first point, same x coordinate as the second point. This will be C, B. So the length of this part is C minus A. Length of this part. The Pythagorean theorem tells us the distance. So the square of this distance is the summation of the squares of the differences of the coordinate. Of the x coordinate, difference of the y coordinate, we take a square, we get distance square. We take the square root, in this way we can find the distance between any 2 points. Now given a polygon, a general polygon, not a regular. We can find the coordinates. Then we can find the distance using the coordinate formula. The distance, we add them together, get the perimeter. So this L1 is the length of the first side, length of second side, and on. The difficult part is how do we find the perimeter, the circumference of a circle. So one method is to use the approximation. So the observation is the length of circumference. So this ratio is constant. we will have a special letter for this. We're doing this pi. So with this formula, the length can be written as 2 pi r. So whenever we have the radius, we can use this formula to find the circumference of a circle. How to find this number pi? Last time we introduced this approximation using polygon. Okay, so this is what the ancient mathematicians do. What we also mentioned this Zhu Chongzhi, some ancient mathematicians. Then a new method to find the exact. There are many different methods to find the pi. Another one called Euler, a very famous mathematician. He gave a formula. If we add the reciprocals of the squares, so first the 1 square, that's easy. 2 square, 3 square, add the reciprocals of all squares, then eventually we get this pi square over 6. So you can see it's different from what we have seen before. Before, we have approximations. We can get better and better approximations, but we can never get the exact value. What is pi? This formula, even though it's complicated, it tells us what the exact value is. So how do we find pi? If we can add all of them, multiply by 6, then take a square root, we get pi. This gives an exact value. Okay, and you will learn more about this in calculus. And in particular, a future course called Fourier. Okay. Before let me check with you. Does any of you speak French? Aaron, do you speak French, Aaron? Okay.
No,
Kira,
I speak Mandarin.
Mandarin. Okay, I know Mandarin. Kira, do you speak French?
I take French at school.
Okay, so if you take French, so this mathematician, so he's a French guy. If he's a US citizen, we may say Fourier. No, yes, Fourier. But if because he's French, in French it's different. Fourier. Okay, so this okay. Okay, so something you will learn in the future. Also, we introduced this degree. The total degree of 360. And the flat degree 180. Okay. In the future, we will use letters to represent angles, but frequently we use a different system of letters. Instead of A, B, C, we use the Greek letters. Okay, Amy, do you know any Greek letters?
Alpha,
Okay, Alpha,
omega,
Omega, okay. And let's see, Jessica. Can you hear us, Jessica? Okay, let me check. Aaron, anything else besides these three?
Gamma.
Gamma, okay. Kira, anything else?
Kappa,
Okay, nice.
lambda,
All right, okay, more than enough, more than enough.
Huh?
We will not use so many. Okay, so normally we will use this Greek letters for angles. You will see. Okay, another popular one, theta. Very often we use this to represent angle variable. Yes, Kira.
delta,
Delta. Okay, yes. So we used that before. So the capital delta and the lowercase delta.
Oh yeah. What about sigma?
Sigma, yes. Okay, so how do we write sigma? So, okay, some is this, but something is very close to 6. To differentiate the sigma from 6, I will go a little bit. So this no, now you see this is sigma, not a 6. Okay, so this represents an angle. Now, if an angle is between 0 and the right angle, we call it acute. This is an acute angle. And between obtuse. Okay, we draw a picture, it will be something like this. With these angles, we now have two representations. Let's start with a unit circle. Oh, maybe I should draw a circle first. So a circle of radius 1. We'll give it a special name, so called a unit circle. Now we have one angle. So this angle corresponds to an arc on the boundary. Use the previous method, we can find the length of the arc. So here again, the ratio between this length of the arc over the angle, this is constant. So when theta increases, length also increase. Theta decreases, length also decrease. This ratio is constant. And in the special case, when theta is the whole circle, the whole angle, the length is the circumference. So now we have the equality. Okay. So the ratio is constant, and we found a special case. So the ratio must be this constant. This allows us to go back and forth For example, let's see what's L 90 degree. Jessica, can you hear us, Jessica? Okay, we'll check with her later. Aaron, how do you find this?
You have to convert it with the 2 pi over 360.
Okay, so let's use the formula 2 pi. Then we'll do a simplification. So this will be 2 pi over 4. Pi over 2. So this gives us the correspondence. For this right angle, oh, not very good. We can say it's 90 degree. Or we can say it's pi over 2. Both works. And this will be more popular in the future. So we call this the radian. So we will call this angle this radian. The radian is in kind of the length of the angle on the unit circle. The radius is 1. This radian, a new term. Let's see what if L pi over 12. What's the angle? Fred, how do you find the angle in this case? I cannot hear you.
Me?
Okay, now it's better.
It's 90 degrees. Okay, this.
Okay. We will use this formula. We will use this formula. Okay, there's some simplifications. we get pi. Sophie, can you hear us? Okay, let's turn on the camera, Sophie.
I can't because my.
Okay. All right. Okay, no worries. Okay. Okay, Jessica. Okay, so now we have this. We learned about the length. Now we go to the second dimension. We have this area. Okay, so first let's set the standard. If we have a square of side 1 and 1, then we see the area would be 1. This is a unit square. Okay. Some of you prefer units. If this is 1 inch, then this will be 1 square inch. If you have 1 foot, 1 square foot. Okay, so whatever your unit is, the area will be the unit square. If you have meters, meter square. Okay, so that's for the area. Now, let's see. I think you all know the result. I want you to give me an explanation why. Yeah, not very good. Three, 5. Okay. Aaron, what's the area of this rectangle?
15 square units.
All right, okay, that's a perfect answer. Angled area 15 units square. Okay, now tell me why. How do you get this 15?
Well, 3 times 5 is 15, but you have to remember the square root because it's something times something.
Okay, so now I'll ask another question. So why the area will be the product?
Because think of it this way, like there's 5 squares on the 5 side, and then you
Mm-hmm.
close of that.
Yes, nice. So because for this one, we can, if this is 5, we can put 5 squares in 1 row. Then we have 3 rows. Now we count 1, 2, 3, 4, 5. 3 of this will be the product. Okay, very nice. So that's the general formula. If rectangle sides L and W. So this for length and width. Okay. Another geometric object called the parallelogram. A little bit strange word is constructed from parallel. So two lines, they're parallel. Parallelogram, we have another two lines that are parallel. We draw a picture. Okay, so it means it has a pair, two pairs. A quadrilateral is a polygon with four sides. A parallelogram is quadrilateral with two pairs. Okay. Then we want to find the area. This one we need to measure the length and the height. Then the area will be okay. The reason for this is that we can make a cut. And we can shift this to there, fill the triangle, the rectangle. This rectangle has two sides, L, because L is what we have, and H. So the area of this parallelogram can be reduced to the area of rectangle. Okay. Another geometric object called a trapezoid. Okay, let me check. Jessica, have you seen this term before, Jessica? Trapezoid.
Yeah.
Okay, so describe to me. What does this mean? What's the geometric shape?
It's a quadrilateral with at least one pair of parallel sides.
Okay, very good. Okay, so now you know that. Let me draw an example. Hopefully, it's not that bad. Okay, that's fine. Okay, so this one will have the top side, bottom side, and the height. And Sophie, what's the area of this trapezoid using these terms? It's fine. If you don't know, that's fine. I just want to check. Have you seen it before, Sophie?
I think so. I don't remember.
Okay, cool. Okay. Let's turn off the music. I can hear the music in the background.
Yeah, because my sister's practicing.
Okay, I see. Okay, that's okay. So for this one, we can make a copy of this, but we flip it over. Make a copy of it. These two are the same. In particular, this will be A, this will be B. Now together we have a parallelogram. Parallelogram, so the parallelogram will be A plus B H. So the area of the trapezoid will be half of it. Very useful formula. In the particular case, when the top side is just a point, you get a triangle. Okay, we measure the side, measure the height. So this is a special case of the trapezoid when A is 0. When A is 0, just okay, so with these formulas, let's draw a general polygon. Okay. It's a general polygon, so to find the area, we can use partition. How to remove this? We can partition this into triangles. We can use our formula to find the areas of each triangle. So we get first area, second area, third area. So the total area will be the summation of the two. The 3, A, 2, A, 3. Summation of area. Sum is fine. So now we know how to find the area of any polygon. Okay, now we put this into test. We have a circle of radius r again. Okay, so this now let's talk about the disk. The disk, a round disk is even better. Okay, again we want to find the area. Okay, I think many of you know this formula. Amy, have you seen this formula before?
To find the area of a circle.
I'm sorry, what's that?
To find the area of a circle?
No, area of this disk.
I don't think so.
Okay, cool. Okay. Fred, have you seen this before? If not, that would be perfect. Aaron, what about you?
I think it's r squared times pi, if I'm correct or not.
Okay. So I see someone nodding. So maybe in a few minutes, we will show that is, okay, area pi r squared. Now I want to see why. Okay, first, so the observation, we use this area is AR. The observation is this ratio is constant. And we wanted to check this ratio is the same pi we had before. Okay, let's take this for granted at the moment. If so, then we have a formula to compute the area of round disk of radius r. It's pi r squared. Very useful formula. The only issue is why. Why the two ratios? One for the length over 2r witness. Why they equal the same pi? Okay, think about it. We will have a 5 minutes break and then we resume at 8:17. Think about this. Why they are the same, the two ratios. Okay, let's have 5 minutes break. Okay, so this is a very important issue. We have two seemingly unrelated objects. One is the ratio of the circumference of the circle compared to its diameter. One is the area of the disk compared to the square of the radius. Why are the two the same? Okay, for the moment, let's pretend we don't know they are the same. So we will give it a different name. Answer. Okay. Instead of pi, temporarily, I use a variation of pi. I put a hat. Put a, we call this, add a hat on it. In the end, we will show these two are actually the same, but at the moment, potentially could be different. So now we have two ratios. We wanted to show the two ratios coincide. Okay, so for this, let me draw two circles. Okay, two circles at the same center. Smaller circle, radius r. Larger circle, I increase the radius by h. So it will be r plus h, the increment. Very small. Okay, now let's see what we have. Let me check. So first we want to find the perimeter circumference of this r. Amy, for the smaller circle, what's the circumference? What formula do you have?
I'm not really sure.
So we can use, if we have this formula, could we use it over here?
Yeah.
Okay, what would you say?
Pi times 2r.
Yes, okay. And Fred, what's the circumference of the larger circle? Aaron, what would you say?
I'd say let's see. Height. Let's see. Pi times 2r plus 2r, I think.
Okay, let me correct myself. I wanted to write 2r, but I had 2 pi. Then it will be 2r plus h. Okay, I correct myself, so it should
Yeah.
be 2r.
Although
Okay.
I was gonna say 2r plus 2h, but like that works too, I guess.
Okay, that also works. And Kira, what's the area of the smaller circle?
The area
What
of the
formula?
smaller circle,
Of the smaller disk.
pi r squared.
Pi r squared. So in the end, we will show it's the same pi. At the moment we use this, because we haven't verified this yet. Okay, so at the moment, we're going to use pi r squared. Okay, Jessica, the area of the larger disk, do you have a formula for it?
Pi r squared.
Okay, this mu radius. Okay, so now we have everything we need. The interesting part, what is the area of the increment? Kira,
Could you do the area of the big circle subtracted by the arrows? No, the area of the small circle subtracted from the area of the big circle.
okay, so the big one, we have a formula. Smaller one, we have a formula. Then this should be the difference. That's what we want. So we will use this delta A for the increment. And we know this will be the difference of the two areas. And plug in the formula. Okay. Common factor. The difference, so this will be r squared. Some cancellation, very straightforward. Then h is a common factor. Okay. Factor it out, we get pi 2r plus h. Okay, now we have a formula for the increment of the area. Okay, let me check. Any question about this step? Jessica, what do you think? Does this make sense? Okay. Sophie? And Fred, what do you think?
This thing.
Okay. Now we will do something unusual. So here, this one. Now we want to unfold it. Okay, I will cut it from the bottom. Then I will unfold this. In this process, if when we unfold this, if we keep the exterior one stretched, then we will get a long strip. Okay, so think about this unfolding process. There are two ways to do the unfolding. One is to keep the exterior one tight, because the interior one is smaller. In this process, we will stretch this a little bit. Think about this as a cloth or something. If we unfold this to the exterior length, there will be stretching. Oops, that's too bad. Okay, so if we keep this top, okay, let's convince yourself. If we unfold this while keep the top side straight, so this will be some stretching. In particular, the result will be bigger than this. Okay, so this gives us one estimate. Let's see if this makes sense. I claim in this process, this is H. Because you can see it's not that flat. In this process, if we want to keep this one straight, then there will be some stretching. So we kind of increase the area. So from here to there, the increment increased, have this inequality. Now the second way, second unfolding, that's our first approach. Second approach, we will keep the interior one. We unfold this, we try to keep this side fixed, the length fixed. Then this will be some squeezing. First time, stretching. Second time, squeezing. There's some stretching. Squeeze. Okay, two unfoldings. One little bit stretching, one little bit squeezing. We have this inequalities. Okay, try to imagine, so this is some kind of rubber over a rubber band. A rubber band, if we cut over here, we unfold. If it's long, with a little bit of stretching. If it's a short one, a little bit of squeezing. Okay, so with this, let's put them all together. We have the exact increment. I have two estimates. I'm going to put all them together, step by step. We have an upper bound. We have a lower bound. And we have an exact formula for the increment. Okay. The inequalities. First, unfolding an upper bound. Second, unfolding a lower bound. Amy, what do you think about this inequality? Does it make sense? Kind of, not that
Kind
really.
of.
kind of. Okay. So the key point is about this unfolding. When we unfold, so this is rubber over there. In this state, it's kind of squeezed. If we release this, there will be some stretching. That's the first estimate. But if we want to keep it very tight, there'll be some squeezing. So stretching and squeezing, two different estimates. Okay, now let's do some simplification. Jessica, can we simplify these inequalities?
I think so.
So you have H is a positive number. If we cancel H, we keep the same inequalities because H is positive. H is positive, so we can eliminate H. Okay, I will distribute the 2 to R to H. Okay, again, R is positive. Let's eliminate, divide both by 2R. By 2R. R. I divide all of them by 2R. Okay, simplify a little bit. One plus H over 2R. Now we are getting very close to what we want. So here the point is that our increment H can be arbitrarily small. Okay, this may be a little bit ambiguity over there, but the point is H, even though it's positive, but it can be how small could it be? How small could it be? So eventually we will let this layer become thinner and thinner and thinner. A very thin layer, the H is approximate 0. Okay, now let's see what happens if we replace H by 0. Okay, so we have this kind of a trivial inequality. This is true only when the two numbers are the same. Okay, so a little bit exhausting. I know it's a little bit, a very long argument, but this is not a trivial fact. It's a highly non-trivial fact. It's not easy, not an easy fact, not an easy fact. And often this is omitted, often omitted. Okay. So the point is the two ratios, one from the length, one from the area, and they coincide. This is a interesting but a lucky coincidence. Okay, so now we can go back to where we start. You can see several pages. We verified the two ratios, one for the length, one for the area. They are the same using this approximation. So we can have one and increment, estimated increment. Now we can summarize. Since we verified they are the same, the length 2 pi r and the area pi r squared. So I have the formulas to compute the length and the areas. Aaron, what do you think of this?
It's very complex.
Okay, I agree. It's not easy to verify this fact. Why the two ratios are the same? This is not easy. Okay. And so this method, you will learn more about this when you learn calculus. In the future, you will learn more about this. So this is not some strange thing. The idea, this is the calculus. In calculus, you will learn more about this, the derivatives. So here, our method is actually the derivative of area. The derivative is length. Okay, something you will learn in the future. So you will see this argument will reappear. All right. Okay, so this is about the complex stuff. Now we learn something more straightforward. So we consider lines. One line, a second line. The second line may be parallel to it. Okay. If they are parallel, they do not intersect. As long as not parallel, it will intersect. So when the two lines intersect, there are several angles we can use. This one, we call this alpha, and this one, we call beta. We can see from the graph, the total angle will be 180. And we call these two complementary angles.
Wait, I thought it was supplementary.
Okay, supplementary. Okay, yes. Okay, sorry. Supplementary. Complementary, supplement. Okay, supplementary. Complementary to each other. They are called supplementary angles. You are right. Okay. And the other two angles, we have one here and one there. To describe the relation between them, let's give them gamma, theta. A special relation. So in this case, alpha equals gamma, beta equals theta. Okay, now let me ask you why. So my favorite question, why? Why alpha and gamma, they must be the same? Amy, what do you think? Could we use this fact?
So they equal each other because so like it's called like a vertical angle because they're both like supplementary,
Mm-hmm.
and then like when you
Okay.
like cross
Uh-huh.
them, they're just like
Okay. I get the idea. Okay, yes. So why? Let's look at the picture. For alpha and the beta, if we consider this line, they are supplementary. Okay, proof. Now, if we consider this red line, beta and gamma, they are supplementary. Well, these two angles supplementary to the same angle, then they must be the same. So from here, conclude because they are supplementary to the same angle, the two angles must be the same. And this is the same thing we can use to prove beta and the theta must be the same. They are supplementary to the same angle alpha. Okay. Now we can consider more lines. Special. In general, there's not a obvious relationship between the angles. There's the angle over here and the angles over there. In some special case, two parallel lines. We can have some relationship between the angles. Okay. And so in this process, we will, so as we have seen before, the proofs, we will learn more about this term, proofs. Okay, how many proofs do we have learned? We have the Pythagorean theorem. We know how to prove that one. We also proved the two ratios are the same. The proofs is that we want to check whether something is true or not. How do we convince others? True or not? Some typical arguments. I'm not sure if you take this algebra course with Professor Drew before. Some of you know, I know. Over there, the proof by contradiction. Okay, let me check. Who has seen this term before? Amy, have you?
I think so.
Okay, so where? Do you remember?
The algebra classes.
Okay. Jessica, what about you? Have you seen this before? Proof by contradiction? No, you haven't. Okay, Amy. So, do you know the Chinese term for this one? Not really. Okay. Okay, Aaron, you know it, I think.
I know how to speak Mandarin, but I don't know how to read Mandarin, so yeah.
Okay. So this appears in the proof that there are infinitely many prime numbers. I cannot squeeze this in. Okay. For a statement like this, it's not easy to prove this directly. So what he try to figure out is, suppose they are the contrary. If there are only finite many, then we get a contradiction. Okay. So this is the one method to prove this, prove by contradiction. Another useful method, mathematical induction. Okay, so a very simple example. Mhm. There are different ways to check this. So one method is, because to check this for integers, there are infinitely many cases. N equals 1, n equals 2, n equals 3, n equals 5, 100, 1000. We cannot verify them one by one. So this mathematical induction is, if we can verify one of them, and you can verify always the next one, this one to the next one, then this automatically imply all the cases. The mathematical induction has two steps. Initial step and induction step. Okay. So this allows us to conclude from the previous one to the next one. The same applies previous one, next one, previous one to next one. This gives the proof for the infinite many cases. Okay, we will learn more about this mathematical proofs next time. Okay, questions? All right, if no, I will see you next week.